So we've proven limit laws for sum and product of functions, and we've done it by proving that the summation function and the multiplication function on the complex numbers, those are continuous functions. Next, we want to do the same thing for division. We'd like the limit law for what happens when you take the limit of f of x over g of x. And because of our prior work, we know that it suffices to prove that division is a continuous map. And so that's what we're going to prove today. We're going to prove that the division map from C cross C to C, which is an operation on complex numbers, is a continuous map on its domain. Now, right away, I've told a little bit of a lie here because the division map, div y x takes the inputs to y over x, doesn't actually have domain C cross C, right? Of course, we have to exclude 0. And so the first change that we have to make is we need to change the domain so that it is actually the right domain. So we're going to take C remove 0 so that 0 is recognized as not a part of the domain. Now, so that's kind of complicated. We need to prove that that's a division, that's a continuous map from C cross C without 0 into C. Now, we have a little bit of a shortcut here. We've already proven that multiplication is a continuous map. So we know that the map that takes yx to y times x is a continuous map. We know that y divided by x is y times the reciprocal of x, which means that the division map is the composition of two functions. It's the composition of first the reciprocal map on x, followed by a multiplication map. So this division map can be treated as a two-step process where first we invert x, and then we multiply by y. What's the point? The point is we already know that that secondary operation is continuous, and so we can focus, because the composition of continuous operations is continuous, we can focus our attention on merely the reciprocal map. So the point here is it suffices to show that the reciprocal map, which takes C without 0 into C, is continuous. And that's much easier because we don't have to worry about the value of y at all. So our goal here is going to be to prove that the reciprocal map from C without 0 to C is continuous. In fact, for reference here, I don't actually have to remove 0 in order for this to be true. If I define the reciprocal map so that the reciprocal of 0 is defined to be the infinity on the Riemann sphere, and I also define the reciprocal map so that the reciprocal of infinity is 0, again on the Riemann sphere, then we actually get a map which is continuous on the entire Riemann sphere, so no problem. But I'm not going to focus on that extension of the complex numbers right now. I'm just going to focus on getting this map continuous on C without 0. Now, we're going to need to use the triangle inequality to do this, which is no surprise. But we're actually going to use the other triangle inequality. So I want to remind you of the two forms of the triangle inequality here. This is the most often used and most important triangle inequality. But we have another inequality relating w plus z to w and z. And that is that w plus or minus z, absolute modulus, is always at least modulus w minus modulus z. Now, this one comes up less frequently. The point of this is sometimes you need a lower bound for the modulus of w plus z, especially when w is a big number and z is a small number. So if you have a big number w, big, of course, in modulus, if you have a big number w and a small number z, which might be an epsilon or a delta that we're working with in a proof, then you want to know that the modulus of w doesn't change very much when you add this very small number. And it doesn't go up very much, but it also doesn't go down very much. So it's greater than or equal to the modulus of w minus the modulus of the small number. So we're actually going to have to use this inequality in this proof. So, all right, we're going to try to show that this is a continuous map. So let's let x naught be some point at which we're evaluating this point, and then at which we're going to evaluate this map, and then we're going to show that the function is continuous at x naught. So let's let epsilon be greater than 0. And then the goal is we're going to try to choose an epsilon. We're going to choose a delta according to the definition of continuity. So delta equals, but I have no idea what it will be, and we'll come back to this later. Then we're going to let x be in the complex numbers, minus 0. And we're going to assume that the distance between x and x naught is going to be less than this delta value that still needs to be chosen. And then we're going to compute, oops, I messed that up. We're going to prove the continuity not of the identity function, but of the reciprocal function. So we're going to try to no, I'm sorry. I'm getting myself confused. We're going to assume this is less than delta, and we're going to try to show that the distance from 1 over x to 1 over x naught is going to be less than epsilon. Sorry about that. Okay, so that's what we really don't know how to do. So let's just start with a calculation of 1 over x minus 1 over x naught, and let's try to figure out what we do. So we're going to take the absolute value, the modulus rather, of 1 over x minus 1 over x naught. And then this is the thing that eventually we want to do a whole bunch of computation, and we want that to be less than epsilon, right? If we can do that, then we'll have satisfied the definition of continuity for this function. Now, there's really nothing that can be done with this thing algebraically except to do common denominator. And so, you know, it might not look like a pretty thing, but we have to do common denominator now. So let's do this. This will be x naught minus x over x naught. So the good news is x naught minus x is in modulus is the same thing as x minus x naught, and that's less than delta. And so already we seem to be in a pretty good way. The bad news is what on earth are we going to do with this denominator? So actually, let's split this first. So I'm going to write this, the numerator I'm going to write for convenience, x minus x naught. The denominator I'm going to split into the modulus of these two numbers. Now, we're trying to show that the reciprocal function is continuous at x naught. And the hardest thing about showing that a function is continuous is the choice, this mysterious choice of delta. Now, I want you to pay very, very careful attention to the proof structure here, and particularly where the choice of delta has to happen within the proof structure. It happens after we've chosen the x naught, because we're not trying to show uniform continuity, we're trying to show continuity at x naught. In fact, this function is not even uniformly continuous. It happens after the choice of x naught, because we're trying to show continuity at x naught. But it happens before the choice of x, because the definition of continuity says for every epsilon, there is a delta such that for every x, if this thing, then we get more inequalities. So the choice of delta needs to precede the choice of x, but it may follow the choice of x naught, which means that the choice of delta can depend upon x naught, but cannot depend upon the value of x. So if we look at this expression, this looks great. This is going to give us a delta, and we get to choose delta. So this we can rig this to turn out to be whatever we want, epsilon over 100, whatever. We can rig this thing to be basically whatever we want. We can rig it by knowing the value of x naught. So for example, if this term weren't here, we could say this would be, well, we could say, for example, this would end up less than delta over modulus x naught. And we could rig this so that delta was equal to epsilon modulus x naught. And then we would just get an epsilon. So if this modulus x were not here, then we could rig the choice of delta so that everything would work out. And this choice of delta would be choosing delta to be epsilon x naught. And this would, epsilon modulus x naught rather. And this would work just fine if this term were not here. So in a fantasy world where this term is not here, we could do that. Delta would be chosen to depend upon x naught, and everything would be fine. Now, you might say, okay, well, if this term is here, then we just need to do the analogous thing, right? We need to simply choose delta to have that x naught in it as well, right? So let's choose delta instead to be, so if this term is here, it would look like this, and then we could do something like this, right? So if we chose delta to be this complicated beast, then it would cancel both of these, and we'd end up with an epsilon. Is this going to work? No, this is not going to work. This is cheating. The reason this is cheating is because the only way I can say that delta is x naught x is if I can make the choice of delta depend upon the value of x. And you can see here from the strict logic, that's impossible. Delta has to be chosen, and it has to work for all x. And so that doesn't make any sense. So we can't possibly do this. So when you look at this thing, this term right here, it looks like we have a symmetry between x and x naught. And it looks like we're almost ready to choose delta. Just choose it to be something so that we get an epsilon and everything else cancels. But we're not there yet, because this is not symmetrical in the x and x naught. The x naught is no problem. The x is a big problem. So what are we going to do? We're going to try to get rid of the x. Now, the x is close to x naught, right? And in fact, we have some degree of control how close it is to x naught. And so an approximate value of x is x naught. We're going to write x as approximately x naught plus a little bit of an error term. So let me show you what I mean. All we're going to do is we're going to add, in fact, I think I want to go down here for this. We're going to take x minus x naught. And in place of this x naught here, we're going to subtract and add, sorry, in place of this x, we're going to subtract and add the x naught. So x minus x naught plus x naught. That seems a little crazy, but let me explain. So we do this subtracting and adding thing anytime we wish to express an approximation with error for a term here. We have kind of lost control of x when it comes to this delta because x has to follow the choice of delta. But we know that x is approximately x naught, and we have full control over the x naught. We can choose delta to depend upon x naught. And so what we're really trying to do is we're trying to say, let's prepare a mode of thinking in which x is approximately x naught, and we use the value of x naught as a substitute for the value of x. Why does this do that? Because this thing can be split now by the triangle inequality into a term, x minus x naught, which is controlled small, and another term, x naught, which is controlled basically constant from the point of view of delta. So this gives us an x naught term, and that gives us an x minus x naught term. So now I'm going to use the triangle inequality here, and I'm going to do so carefully. So this is going to be less than or equal to, let's apply the triangle inequality and see what happens. So the numerator is going to stay the same. And in the denominator, I left off an x naught here. In the denominator, we're going to get, let's see if this works, x minus x naught plus absolute x naught. I'll parenthesize that because the whole thing needs to multiply absolute or modulus x naught. All right, how'd I do? Did I do a good job or did I mess it up? Well, the triangle inequality says that the modulus of a sum is less than or equal to the sum of the moduli. And here I've got a modulus of a sum, namely the x minus x naught plus the x naught. And I've split that into the x minus x naught modulus plus the x naught modulus. So far so good, right? Well, maybe not. This is happening in the denominator of a fraction. And so, yes, the triangle inequality goes this way, but what I've done here is I've potentially increased the denominator of the fraction. And because that happens in the denominator of a fraction, then the denominator is going up. The fraction is actually going down, potentially. So I should have this. Now, I can't bear this symbol in this proof. That won't work, because if I have one symbol like this, then how am I ever going to prove that it's less than, that the original thing is less than epsilon? So I can't have that symbol. That's not going to work. And that means that my use of the triangle inequality is not going to work either. So let's think this through carefully and see what we need. We absolutely have to have symbols directed this way. That allows, so what that means is this whole fraction is allowed to grow. If the fraction is allowed to grow, what is allowed of its denominator? The denominator is allowed to shrink, okay? So I should not be using this thing. This is a mistake. I should be using this thing. This is the inequality that I want here. So what I'm going to do here is I'm going to substitute here absolute one thing minus absolute the other thing. And remember how I was talking about W big and Z small? I want to take the big thing minus the small thing here so that this works out well. Which of these things is big and which of these is small? Well, x naught is entirely unpredictable. I don't know. X minus x naught is less than delta, and delta is presumably small. And in fact, we will have control over the size of that. And so, we can, I mean, once we choose the value of delta, we can assert with some confidence that that thing is small. So what I'm going to do is I'm going to treat x naught as the large and x minus x naught as the small, and I'm going to apply this inequality. Now, so what I'm going to do here is I'm going to get modulus x naught minus modulus x minus x naught. Now, is that even a positive number? Because if that's a negative number, then I'm going to be in big trouble here. Then this inequality, like I know that this is positive. If I have accidentally made this denominator negative, then this whole fraction will be a negative number. And that's bad because that means this inequality certainly cannot be true. So I'm allowed to decrease this, but in order for this inequality to even be true, it has to stay positive. So do I have any reason to believe that this is positive? Well, I mean, really, no, not yet, but I can force it to be positive. So this is the modulus of x naught. All I need is for this thing to have a modulus which is really which can be related to that. Okay, so I need this modulus to be not much bigger, not any bigger than that, so that it won't be negative. In fact, I'd like it significantly smaller. Here's where we're going to start using our freedom about delta. This thing is no more than delta, and so by controlling delta, I can control this so that this is not greater than the modulus of x naught. How will I want to control it? I want delta to be not even half. I want this modulus to be not even half as large as this one, so that not only is it positive, but it's we haven't subtracted more than half of the original thing here. So here I'm going to choose delta so that preliminarily, I'm going to choose delta to be modulus of x naught over 2. So preliminarily, let me actually leave a little space here. Modulus x naught over 2. So I'm choosing this so that that term will not be too big, so that I know that it's significantly less than this term, and this thing will remain positive. All right, so that's something. That's something. Now, can I use that to simplify this? Well, yes. So if this thing is less than half of this thing, then the result of subtracting them is at least half of this thing. So let's write that. So this thing here, this thing in parentheses, is going to be, because this is less than half of that, then the result of the subtraction will be greater than or equal to this x naught. So let's write that, greater than or equal to half of that x naught. So half modulus x naught. And then I've got the other modulus x naught here. So let's see whether I've got my inequality correct. I need it to be this way. Let's see whether I've got it that way. So this inequality allows the thing to grow. If I'm allowing it to grow, then I'm allowing the denominator to shrink, right? This thing here is at least double that. So I've subtracted at most half of that. And so by replacing it with half of that, I've allowed it to shrink. So the denominator is being allowed to shrink here to half of this by subtracting less than half of it. Then the answer to this subtraction will be at more than half of it. And so half of it is a contraction, which will cause the fraction to expand. Okay, so that gives us a simplification here. And notice we've paid a lot to do this, but now instead of absolute x in the bottom, I have absolute x naught, which is really what I need. Now, all I need to do now is rig the value of delta so that this says epsilon. And so what I'm going to do is I'm going to say that's going to be less than or equal to delta. Well, that's going to be less than delta over 1/2 x naught squared, modulus x naught squared. And what can I choose delta to be so that everything will work out well? I can choose delta to be epsilon times 1/2 times modulus x naught squared over, and then we'll get the same thing down here. So if I rig delta to be this, then I will get all the cancellation that I need, and I'll end up with epsilon, which is exactly what I need. Now, can I choose delta to be this and also choose delta to be this? Well, no, I can't necessarily, I mean, I've only got one delta, right? So I can't choose delta to be this at the same time that I'm choosing delta to be this. But I can choose delta to be less than or equal to both of those values by choosing delta to be the min of this value that we need and also this other value that we need. And so long as delta is the min of those, then delta is indeed going to be less than or equal, that should have an epsilon in it. Then delta is going to be less than or equal to this requirement, and is also going to be less than or equal to the requirement that gives us this statement, and this statement too. And then all of these inequalities will become true. And we've got a strict less than. So I've proven here that the difference in the function outputs is strictly less than epsilon, provided that the difference between the inputs is less than delta, which establishes continuity for the reciprocal function. So this gives us that the reciprocal function is continuous. And again, by composing it with the multiplication function, we can deduce that the division function is continuous. Not, of course, on all of C cross C, but at least on its entire domain, which is all that we really need.